Hello. In this video, we will be talking about the Bitcoin, which were seized by the FBI. So we can see here the official statement by the FBI. So we can see here that 2.3 million Bitcoin have been seized by the FBI or whatever. Currently valued whatever. These funds represent the proceeds of a May 8th ransom payment to individuals in a group known as DarkSide. So all of that is not important to us. The entire thing here is the important part is they did not mention how they got the private keys, so they're not mentioning any of that. Oh, yep, they're just mentioning here, as we can see, that for which the FBI has private key or the rough equivalent of a password needed to access as is accessible from a specific Bitcoin address. This Bitcoin represents whatever, boring. So the thing here is they are not saying how they got it, and I highly doubt they cracked more or less. Well, the news more or less is the FBI hacked Bitcoin, but I highly doubt that they're able to get the private key of any account. So we'll be talking about that in more detail. But first, let's look at the blockchain explorer. So we've got here the address that it was sent from. Here's the main address with where lots of Bitcoin got there. And from DS75, we can see here that from this account, this is the account where I think the FBI got the access to, and they recovered these 33 Bitcoin here. So we can see these are the 33.69. So they were mentioning here that they retrieved like 63.7, I think. I just have to look it up one more time. And there it is. They mentioned here that they see 63.7 Bitcoin, so that would be exactly that here. Okay, so that was sent to their own wallet address, so this was sent there. And right, that's the account the FBI is currently having in custody. Okay, so if we quickly go back here, we can also see that the 63.69 Bitcoin which were sent were multi-signed, weren't they? Well, wait a second, I have to load all the rest. So no, my bad, I will... Alright, yeah. They were multi-signed, so all of these Bitcoin which were sent here, they were all multi-signed. So meaning that they had 2 out of the 3 apparently private keys. So right. So this also suggests the part there that this might have been a custodial wallet. So it could be the case, so I'm just making the case here, that the hackers were having a custodial account, meaning that there was a platform. So it could also, for example, if you have Coinbase, so if you have a Bitcoin address on Coinbase, you actually do not hold more or less the private key. Coinbase is managing it for you. Meaning that if it's a private company in US jurisdiction, I can't pronounce it, restriction, yeah, then obviously FBI can go there, can tell me, yep, shut down the servers or shut the service down for now and give us the private keys. And that's my theory about it. Please also correct me if I'm wrong on any of that. I could be completely wrong about all of this, but this is just my take on all of it. So that's what I think happened. So the multi-sig thing supports the thing. I don't think that this, or maybe also it was a criminal organization, but I don't think the FBI would have been able to retrieve those unless they were able to get access to the computers or whatever. So who knows? Maybe also the hackers stored their private keys on the computer as plain text or whatever. But I doubt that. I highly doubt that. So well, who knows actually? But going to the important part here, that the FBI is not able to access any account at will. Regarding that, we have to first, so in order to understand all of the clearer, or more clearly, is we will have to look at the account generation part here. We'll look at the technical background, okay? So whenever a new account is being created, we use the ECDSA algorithm. So we can also look into that quickly. We see the elliptic curve digital signature algorithm. With that algorithm, a private and a public key is being generated, okay? So we've got then or private and public key. And the important part is basically this generation process here. So depending on how good the ECDSA algorithm is, that easy or that hard it is basically to brute force or target an account. Okay, so the main mission is to get the private key. The thing is, the private key will never be sent because actually this private key never leaves the machine. Because usually when you sign something, you're using, for example, when we create an ECDSA pair, we get a private and a public key, and when we send, so we can see perform SHA 256 hashing on the public key. So that's not really important because we're just hashing the public key. It's not really interesting at all. So yeah, so this is just a process how the final address is being generated. So we've got the checksum and all of that, and so we can generate it to that. But the part here is, so you cannot go back from any of these steps because you cannot from the public key. The public key is unimportant. You can't do anything with the public key. This key here never leaves, more or less leaves the machine, meaning that part here is what the FBI would have to get. And there's also an article, so there is a scientific paper on that regarding the ECDSA weak randomness, so ECDSA weak randomness in Bitcoin. So this is not a problem which persists anymore. This problem has been fixed, but it's very important how new addresses are being generated. So they're currently like 0.48. Yes, we can see it here. That after analyzing Bitcoin transaction data set from January 2009 to July 2017, we find that there is still approximately 0.48% of transactions involving this vulnerability. So there are a few transactions, so more or less also, well, from the transactions there are the accounts, which have a vulnerability, and 1,331 private keys have been compromised. In addition, the transaction related to some involved addresses have a common pattern, which gives us a clue that the spam transaction attack may take advantage of the ECDSA weak randomness. So there are attack vectors, there were security issues, but overall it is so they have been more or less for now been well resolved. Okay, so they were also able to do the same for other blockchain technologies. So they made a scientific paper on that, so we can see there. They also published the source code on it, so you can check it out on GitHub. But basically I just want to highlight that the cryptography part, in as far as I can assess that with my limited knowledge, is completely safe. So the FBI is not able to randomly seize your funds, but I think they intentionally leave it in the unclear, so to let also criminals think like, no, we shouldn't use Bitcoin anymore. By the way, I hope all of you know that Bitcoin, as also many other blockchains, are a public blockchain. So meaning that anybody can transact where the money goes to. So any transaction can be followed. So you click just on it, and you just give me your public. So you just give me your Bitcoin address. I can look it up and then see where you have sent your Bitcoin to, received it from. So yeah, it's a public blockchain. Anybody can check that. So that's very important. So it's a common misconception. Bitcoin is not private, or it's not untraceable. It isn't. Right. So the last part I would like to mention here is now that right. So no system is unhackable. Okay. So there are always vulnerabilities there, but with the current state, I would say the chances are still pretty low that Bitcoin accounts can be like quote unquote hacked. So for that currently, so as soon as we get more computation power, then obviously the possibilities get limited. So encryption always relies on it that the problem is so big that it's impossible to solve it with much computation power. So for example, you can also look in the ECDSA algorithm, how it's basically generated, and then check out all the possibilities. So we've got the ECDSA. We can also check it here. So let's have a quick look at the elliptic curve digital signature algorithm. And we can see here that, okay, right, so that there's all the mathematical stuff. I also can get into right now. The thing here is how, right, so there's also the part about security, then also about certain problems which were found in OpenSSL with it, and they have been fixed. Right. But right, so can't verify it right now. But okay, we can just see here that the size of the ECDSA private key would be 160 bits, whereas the size of these private keys, at least we've got here. Right, we've got the ECDSA private key is about 160 bits. And right, yeah, so that is a lot. So you just have to go through all the states, so it's rather simple. If we have 160 bits, so each bit can have the states 0 or 1. That's quite simple, isn't it? So meaning that we take 2 to the power of 160, and these are all the possibilities. So 2 to the power, if I can find it, to the power of 160, and we get a huge number here. 1.46 times 10 to the power of 48. So that is a large number. So these are all the private keys, and you would have to check all of those against one address and try if it works or not. And currently the computation power is not there, at least as far as I'm concerned. I could be wrong, so they could be much further. We don't know that, but as for now, nothing has really changed. Everything is the same. They were just able, in my opinion, to gain control of a custodial wallet. So there was a wallet service, like, for example, just imagine the hackers were using something like Coinbase. Then the FBI busts in, so they can track it and see, okay, this one belongs to you, whatever. Okay, well, right. So we have to shut down. We will see. Give us a private key, and that's it. So that's my theory here. But like I said, I could be wrong. I'm just trying to make sense of all of it. And right, so, and I also wanted to give you some technical background. So I would recommend also looking a little bit into the entire encryption thing. So also into the algorithms behind the technology. There's also a nice generation part here. So we can see how a Bitcoin address is being generated. So as you can see here, we take the public key, use the SHA-256 hashing algorithm. So then we get that address, we perform a RIPE-MD 160 hashing of the resulting hash of SHA-256, then we get that one. Add version byte in front of the RIPE-MD 160 hash, so we add a 00 before that. And what else is there? Then the part there is, I think, equal. To change something? No, I don't think so. Okay, right. So then what else do we do here? Perform SHA-256 hash and extended remedy with 160 result. So we hash the entire thing here again, apparently, with SHA. And oh, my bad. No, we concatenate a thing here, but it's not that important. But never mind. Then perform SHA-256 hash on the result of the previous SHA 256 hash, and take the first 4 bytes of the second edge, whatever, and then we have the checksum and whatever, and then there's the final address. Okay, so that's basically the process how all of it works. But the important part you have to look into is the ECDSA key, because that's the most important part here. So right, so you can also look for, just Google a little bit. There are great scientific papers on that. So you just enter ECDSA vulnerability, so you can do it in the vulnerability, and just look if there's some new info out there. What else you can see if there's something more recent which hasn't been fixed, more or less. And right, so we can see the OpenSL. Okay, there's a Minerva attack. Minerva attack. Right, so this is from 220, isn't it? Yeah. So, right, so that's basically my entire take on it. So, yeah, right, so thanks for watching, and see you in the next video.